Well, it looks like nothing got recorded from the screensavers, so but anyway, before we move on, do we have any questions, concerns? Okay, so this was the last assignment that we're going to have in this semester before the midterm, okay? So today we're going to be announcing the midterm assignment. Yes,
I actually had a quick question.
Yes.
I couldn't figure out how to make the time, like, not military time.
What is not military
so,
time?
Military time, it goes from, 1 to 24 hours.
You mean European style?
What? European style. Oh, sorry, I call it military time.
It's fine, it's fine.
I couldn't figure out how to get it, like, AM, PM. Is that a different setting, or is it just not?
You can do a very numerical rule. You can say, take the number that hour gives you, okay?
Yeah.
And then you can say if it's greater than 12, then it's PM. If it's less than 12, it's AM. And if it is greater than 12, then just subtract 12 from it. Right? Okay. So today we will be discussing, by the end of the class, we will be discussing the midterm assignment, which is going to be a video game, okay? And we're going to spend 2 weeks working on that. And also, as a reminder, I sent you an email today discussing that I will not be able to come next week and teach the class. So in order to make up for it, what I have planned is to have a makeup session this Saturday, okay? Next class was going to be a full hands-on work from the bottom up, programming 2 video game examples. One is going to be Pong, and the other one was going to be Space Invaders. So I plan on doing that same thing this Saturday, from 2 to 5:30 in this room somewhere in a building. I already gave you the details. So I wish as many of you can come as possible. But if you can't come, then the whole thing is going to be recorded, so you will be able to look at it afterwards. And I'm also, because of this inconvenience, the video game assignment is going to be due in 2 weeks. If over questions in the forum I see that things are maybe not going that well, I may consider just postponing the whole deadline just another week, so that we can have time on one-on-one and make sure that the video game is nice. Because I really want the video game to be like a super nice assignment and something that really goes into your portfolio. So I want to make the best out of that time. Okay? Any questions about that? Yes?
What's after the video game?
After the video game, it's just final project. Nothing more, nothing less, no more workouts, no more assignments, just final project. Okay? We will talk about that the week before spring break. Okay? I will explain what the scope of the final project is going to be, what kind of projects can we work on. I will give you examples. I'm thinking of inviting some students, former students, to come here and present the projects they did for the class. And then we will have some form of lecture where I will probably talk about media or data, and then we'll go for spring break. Okay? How does that sound? Yeah? Good. Okay, so today what I want to discuss is further enhanced ways of doing animation and working with graphics in processing. Okay, so one thing that I would like to remind you is that so far we are very acquainted. With the idea that processing is like a 2-dimensional window that has a coordinate system that we discussed the very first week was a bit strange, right? Because as opposed to X and Y from the bottom left corner, which is what we're used to, now in graphic-oriented environments, the main origin, the 0, 0, is usually the top left corner, and X is pointing this way and Y is pointing that way, okay? And that is the reason why when I have my processing window and I draw a rectangle from 150, this is 150, and the width is like this, and the height is like this, right? Because my origin of coordinates is here, and because the orientation of that origin of coordinates is positive X and positive Y, okay? That's the default, which gives me very orthogonal geometry. However, as many things in processing, this can also change. And it can be actually very useful to change it for many reasons that we will see today. Because, for example, if I wanted to draw a rectangle that instead of like this, it's inclined, for example, 30 degrees, how could I do that right now? I would have to figure out like a way to draw in a quad, but the quad I would need to like manually somehow figure out the coordinates of the 4 points. It's kind of messy, right? So what we're going to look at today is ways of working with the coordinate system in order to be able to customize where and with what orientation things on my screen are drawn. Okay? And how is that going to work? Well, the idea is that, and I'm going to open a new processing sketch, and I encourage you guys to join me on that. What I'm going to do is, well, let's start by creating the typical structure that we have for any, actually, no, I'm going to take that back. Let's work static for a second. If I have a large window, for example, a 600 by 400, and I clear the background a little bit, and then I draw a rectangle from coordinates 150 with 75 and 25 of size, the result that I will get is something that I'm already expecting, which is the rectangle in those coordinates and with those dimensions, okay? However, what if I wanted to rotate that rectangle? Processing allows me to do two operations to change where and how the coordinate system is displayed on the screen. So, for example, one thing that I can do is, if my coordinate system is here, and I want to draw a rectangle here, I need to know the coordinates of this point. However, if before doing that, what I do is I move the coordinate system from wherever it is to somewhere on my screen, for example, here. If I do that, and this point becomes the new 0, 0, and this becomes the new positive x, and this becomes the new positive y, then any rectangle or any geometry that I draw after this transformation here is going to take 0, 0 as this point here. Okay? This movement of the coordinate system is called a translation operation, translate, and it's done with the translate operation. So here, look at what I'm going to do. If I translate my coordinate system to the point with coordinates 100x and y equals 50, and then I draw the rectangle, instead of drawing it in coordinates 150, now I draw it in coordinates 0, 0, the rectangle is going to show in the exact same place, because at this point in the execution of the program, here, right here, my coordinate system is right here. 0, 0 is this point here. Does that make sense? What are the coordinates of this point then, now? Negative 100 and negative 50. Because 0, 0 is here. Does that make sense? And something else that I can do is like, okay, once my coordinate system is here, I can always move it whenever I want. But what I can also do is I can rotate it. So for example, if once it's here, I rotate my coordinate system 45 degrees, then this stays as 0, 0, but the new direction of the x-axis is this one, and the new direction of the y-axis is this one. Therefore, if I draw a rectangle at 0, 0, now, how is my rectangle going to show up? Right? let's try that out. Here, I can translate my coordinate system and put it in this, and then I can rotate my coordinate system 45 degrees. However, remember that natively, and this is pretty much the same for all programming languages that are screen-oriented, angles are not measured in degrees, they're measured in radians, okay? And I will remind you later what radians are. So if you remember, 360 degrees are 2 pi radians, okay? So 45 degrees are how many radians? Pi divided by 4. So I'm going to rotate this pi divided by 4, and then I'm going to draw my rectangle. And you can see that the rectangle is drawn from 0, 0, but this is x and this is y. Okay? If I did not remember radians, I can always use the radians function in processing that, given a number in degrees, it turns that number into radians. Okay? So this is the exact same code. I'm turning here 45 degrees into radians, and then I'm feeding that to the rotate function. Okay? That makes sense? Okay. Two things that I would like to notice here. First, if you remember, in mathematics, usually when we had x and y, angles were measured positively this way, right? But now, because our coordinate system is kind of flipped, remember that positive angles are always measured positively from x to y. So positive angles now are measured this way. That's why positive 45 is rotating clockwise instead of counterclockwise. Okay? The other thing that I would like you guys to notice is that when we do spatial transformations, which is what's happening here, the order in which we do those operations actually matters a lot. Okay? So imagine that I translated 100 and 0, and then I rotated 45 degrees. I'm moving the coordinate system here, and then I'm rotating 45 degrees. Okay? But what if I flipped the order? What if instead of rotating first, what if instead of rotating last, I rotated first? Why does this matter? Exactly. Because remember that any transformation that you do on the coordinate system is going to be applied to whatever the coordinate system is at that point. So they accumulate one after the other. So for example, what we've done before is we move here, we move 100 units, so the coordinate system is here, and then we rotate over this coordinate system. However, if we flip the order, what we're doing is we are creating a coordinate system here, and then if we move it 100 units in the x direction, we're moving it in this x direction here. So we're moving it here. That's why before we had the rectangle here, and that's why now that we have flipped the order, we have the rectangle here. Order for spatial transformations matters a lot. Okay? Another thing that we can do on top of that is that we can scale the coordinate system. Okay? I can scale the coordinate system by 5 so that anything that gets drawn on that coordinate system is drawn 5 times larger, because I have increased the size of the measuring of that coordinate system. And I want you guys to notice as well that even the styles are scaled up. So the thickness of this rectangle is now 5 pixels instead of 1. Okay? But remember, all transformations, one after the other, they accumulate. And if you're not really sure of which one should go first, I recommend that first you try translation, then you try rotation, and then afterwards you try scaling. Usually, 75% of the times, that's what you want to do. Maybe not for special reasons, but usually that's the order that you may want to follow. Okay? Just a rule of thumb. Any questions? Okay.
Are these like absolute values? Like, if I say rotate 45 degrees,
Mhm.
and I say rotate 0, that's not going to change. Or is it when I go back to 0 degrees?
No. It would be always an in addition to how the coordinate system is. So they're not absolute values, they're relative values. So what Antonio is asking is like, okay, I rotate 35, I move here, and now I say rotate 0. Is this going to go back like this? It will not. Because what you're saying is, however this is, rotate it 0 degrees in this direction. And that is nothing. 0 is not the absolute position. It's like an increase on top of whatever it is at that point. Okay? Okay. One last thing. I have this, and then I have another rectangle that I want to draw at 200, 300, blah, blah, blah. Oops. Actually, that one doesn't even show up. Okay. So, what happens? Here, I've done some transformations, and I've drawn that one rectangle here, which is inclined, and that is fine. But imagine that after that, somewhere, I wanted to go back to my normal coordinate system and draw this rectangle at normal coordinates. So 200, 300, and then tiny here. See what's happening here? This rectangle is also being affected by the changes that I've done in the coordinate system, and it's showing somewhere weird here. It's not back to the normal grid. Okay? How could, for this rectangle that I'm drawing afterwards, how could I undo those transformations and go back to a regular 0, 0, x and y like usual? For this one, what do you guys think? Parker?
Repeat the translate and rotate function to negative value.
Okay, that is one way to go. I could say, well, I'm just going to copy paste this thing, and I'm going to undo it by using negative values. Okay? But that I've done there is not going to work. This is not working because remember that the order matters a lot. So I would need, if the last thing that I did was a rotation, the first thing that I want to undo must be a rotation. Okay? So that is the first thing. These are the right coordinates of that point. Before, it was not where it should. So if I first translate and then rotate, I need to first unrotate and then untranslate. Does that make sense? However, just as when we did stroke, fill, whatever, and remember that we could do a lot of changes in the styling of how things are drawn, but sometimes we wouldn't really know exactly what the previous value was to go to. Something similar happens here. When I draw a rectangle, I may actually not know, or I have lost track of like all the rotations and all the transformations that have happened here. Okay? So I may not be able to actually pull the values to undo the transformation manually. If that is the case, what do you guys think I might be able to do? Well, how did we do it for styles? Have we talked about push style and pop style? No? Okay, my bad. We should have talked about that. So, I think we have, no? Okay. Well, it turns out that processing comes with a nice way of, I'm gonna call, saving the current state of the coordinate system and then pulling it back. Okay? The idea is that before you do any transformation or any changes in the transformation, you can call a function called push matrix. And what push matrix is going to do is it's going to save the current state of the coordinate system. Okay? So processing goes somewhere in memory, and at this point saves that here the coordinate system was at 0, 0, and it had this particular angle. Okay? Then I can do as many transformations as I want. I can draw the rectangle with those transformations applied to the coordinate system. And afterwards, when I have finished and I want to go back to before, I can call the opposite function, which is pop matrix. And pop matrix restores the coordinate system that was saved in the last push call. So what pop matrix does is it looks at what processing saved last time push matrix was called, and it brings it back on. Similarly, processing comes with another pair of functions called push style and pop style, which are super useful for the exact same idea, but with styles, with a fill color, with a stroke color, with a stroke weight, etc. You can save the styles, make your changes, draw your circles, and then restore whatever style was before by popping its style. Okay? So if I run this code, this rectangle is being drawn with our regular 0, x, and y coordinate system, the default one. Okay? Because at this point, this coordinate system has been restored. Jerry?
Can you put something there so you have like profile 1, profile 2, profile 3?
No.
Or is it just like before and after?
It's before and after. But you can accumulate. For example, you can push matrix 1, 2, 3 times, do changes, and then you can pop it back 3 times.
Oh, so it's like a nested.
It's like a nested, you can nest them together. Ooh. Okay? Any questions? Okay, so what can we do with this? Well, this is the idea that I've just discussed, the idea of the difference between translating things and rotating the coordinate system. And remember, when you're doing what you're rotating, is you're rotating the coordinate system based on whatever it was, and that transformations accumulate one after the other. So if I first translate and then I rotate, I'm going to rotate over the translated coordinate system. And the order matters a lot. Okay? So for example, if you go to the samples in this, if you go to the samples on this, on the folder, you can go to the transform push matrix, right? And here, what you have is a for loop where I'm creating a lot of random x, y, z coordinates, and then during each for loop, I am pushing the matrix, so I'm saving the coordinate system, the 0, 0, 1. Then I'm translating, rotating, I am doing some changes, drawing the rectangle, and then popping everything back. Okay? Why is this important? Because if I didn't do push matrix or pop matrix, something bad would happen. And it would be that only from maybe like the 100 squares, only 2 of them show up because I am translating. And then I'm translating again, and translating again, and translating again over and over and over 100 times, so that I have rectangles going all the way down to 5 levels down in the basement. Because accumulations are happening on top of the previous ones. I pop and I push the matrix so that I always revert back to, on each for loop, I always revert back to 0, 0 for the sake of drawing the next rectangle. Okay? Jasmine?
That's still some of them overlap, right?
Yeah,
But
but
that's just random.
that's just random.
Okay.
Yeah. Overlapping is a different story. Mm-hmm. Similarly, if we, but maybe you don't want that to be the case. Maybe you want the effect of the translations to accumulate on top of each other. So for example, that's what I'm doing here with a for loop. where I'm going over a grid of rectangles, and the rotation between them responds to the location of the mouse in the X direction. So as soon as I move, you can see how the rectangles start rotating, and they rotate, and each one of them increments a little bit over the previous ones, creating this really interesting accumulation of the patterns, right? Which is a very nice and playful effect. Okay? You can take a look at the examples later. Is this still recording? You can take a look at the examples later. Okay? If you want to know more about transformations and matrices, you can take a look at the tutorials here at Transform 2D. Okay? Questions? Okay. Are you ready for some trigonometry? Finally? Huh? No? Never? Okay. Who watched the video that I sent the other day? Dan Schiffman's video on trigonometry. Oh my God. Okay, then this is on you. Okay, let's recatch a little bit of basic trigonometry, okay? And the main idea of why I'm going to do this is because we want to solve the following problem. And can you point that to this whiteboard here? Can you point that here? Yes. Just there you go. Hi. So the goal of why we're going to do some trigonometry today is because we want to be able to figure out a new way of doing coordinate transformations and creative movement. The only way we've been able to do movement so far before is by, we have a coordinate, right? And the movement in 2 dimensions of this point, or this circle, or this car, or whatever, has been because we knew that it had velocity x and velocity y, so we knew the velocities in both directions, and therefore every frame we knew that this object was moving like this, and then like this, and then like this, and then like this, right? Sorry. But this, to my taste, is a little bit artificial, because when you're driving a car, you don't know the velocity in north-south direction and your velocity in east-west direction, right? That's not how cars work. You know your velocity in whatever direction you're going front, and you know the angle at which you are rotating with your steering wheel. That is a much more natural way of understanding movement. So for us, another way of working with movement, which will often yield better results and will be much more useful for many cases, will be if we want this circle or this point to move every frame. We want it to move, for example, 10 pixels. But we want that movement to be at an angle of 30 degrees. So if we know that this is an angle of 30 degrees, and if we know that this distance is 10 pixels, and we know the coordinates of this point where it is right now, my question here is, what are the coordinates of this point in the next frame? If I know how much it's moving linearly and the angle at which it's moving on the screen. How do I know that? Ta-da! Trigonometry. Okay? Let's refresh a little bit of trigonometry, okay? I learned trigonometry in a different country, so the way we remember rules when mnemotechnic rules is a different. I think you guys go for like this like volcano name, Krakatoa, Sokotoa, something which I don't even know what it stands for. But if we go back to the basics and we assume that we have this triangle here is a square rectangle triangle, which means that this angle is 90 degrees, right? We remember from trigonometry that there was a relationship between the length of these 2 sides, the shortest sides, and the length of the longer side. What was that relation? Who remembers that relationship? Okay, we're good. There's hope. There's hope. Who was the guy who invented this? Pythagoras. Oh, there's hope. We're not as bad as I thought. Okay, good. Which means that if I know these two guys, if I know A and B, for me it's really easy to know Z, right? Because then C becomes the square root of A squared plus B squared. Okay? Why is this useful? Well, let me give you guys an example. Let's say I have a point here, and the coordinates of this point are 10 and 10. And this point here has coordinates 15 and has coordinates 14 and 13. Okay? What is the linear distance between these two guys? How far apart linearly are they from each other? If this was the processing window, I could do the following. I could draw like a virtual rectangle, like this, which starts to look very similar to that, right? And it turns out that if instead of calling this B, I call it the difference in the x coordinates of these 2 points. If I call this the difference in the y coordinates of these 2 points, right? And if I call this the distance, so what does the distance is equal to? Is equal to the square root of the x squared plus the y squared. And what is the x? Give me the number. It's 4, because it's 14 minus 10. So 4 squared plus 3 squared equals the square root of 25, which is what? 5. So the distance is 5 pixels. Aha! So Pythagoras was useful. Wow. So the first real-world application of the Pythagorean theorem is that it's very easy to find the distance between 2 points whose coordinates are known by just applying the Pythagorean rule, okay? Which is what processing is doing inside, somewhere in the core engine, when you call the dist function. You're just doing the square root of the difference of those two coordinate systems, okay? Does that make sense? Okay, but the problem we're facing here is not exactly finding the distance. What we actually want to do is the opposite. I know where I am, I know this angle, I know this distance, but I want to know the coordinates of this point because I want to move in that direction. So if we want to figure that out, it's going to involve like looking at the problem from a different perspective. And what is that perspective? The perspective is that it so happens that for triangles that are squared, and that's a really bad square triangle, if we know this angle, and we call it alpha, okay, and we know the longer, and we know the sides here, through trigonometry, we know that there are certain relationships between the sides of this triangle and the angles of this triangle. They are defined by sines and cosines and tangents, okay? And I think that's where the Krakatoa, Sakatoa, whatever kicks in, okay? So, for example, do you guys remember what the sine of this angle was equal to? A over C. Where are you getting that from?
Okatoa. Opposite over.
Please, please.
Hypotenuse.
Hold on. Can you?
Opposite over hypotenuse.
Opposite side, which is this one, the opposite side to this angle, over the hypotenuse. Okay? Which means that if I know the angle, and I know one of these guys, actually this is, exactly, sorry. Okay? Which I means that if I know the angle and if I know the hypotenuse, then for me it's very easy to say, well, then this guy, A, is equal to the hypotenuse times the sine of the angle. And the sine is a function that we know. If we know that it's 45 degrees, we know that the sine of 45 degrees, I don't remember what it is, like square root of 3 divided by 2 or something like that, right? No?
Sine 30?
Sine of 45.
Root 2. No,
Of
root. Yeah, you're right, yeah.
Root of 3 divided by 2 or something, right? Okay, what about the cosine? The cosine follows a similar logic. The cosine of the angle, this one is the, what is this side? Then adjacent side divided by the hypotenuse. Which means that if I want to know what is the length of this, I can just find it by doing the hypotenuse times the cosine of the angle. Okay? Okay, so quite simple. As you already know, we create a setup, draw structure to keep the program alive, and then I create two variables, x and y, that I initialize in the global scope, and I give them their values after the size function, and then every frame I draw an ellipse on those x and y coordinates, and then I increase the position of x and y by the velocity x and the velocity y. Okay? And then I would do the whole like bouncing and blah, blah, blah. But since we're going to change that, I'm just lazy today. I'm not going to write that. Okay? So, of this basic framework, what I would like to do then is I'm going to forget any more about having the two different velocities. But what I'm going to work now is with one single velocity, linear velocity, straightforward, and then with an angle in the two-dimensional space. Okay, so I'm going to cancel these two variables here, and I'm going to write two new variables. For example, speed, that I'm going to start at 1, and angle, which I'm going to initialize at, for example, 30 degrees. How much is 30 degrees? It's pi over 6, I believe. But if you don't remember, you can just say radians 30 degrees. Okay? Just for the sake of, I'm going to go for pi over 6. Okay? If that's the case, then here, I cannot increment x and y anymore by velocity x and velocity y. By how much would I need to increment x and y? So should I do this? You think so? I kind of disagree. Because look, we're not going on 30 degrees, we're going on 45 degrees. Because we're using one value of velocity for the two directions. Every frame, now that we know where the ball is every frame, and we know how much in units it should move, but we also know the angle. Now what we need to do is we need to figure out every frame, what is the increase in the x direction, and what is the increase in the y direction with the trigonometry rules that we have discussed previously. Okay? So every frame, we're going to have to calculate based off the angle and the speed. We're going to have to calculate what's the increase in the x direction and what's the increase in the y direction. And how do we know? How do we do that? We can, for example, here, every frame we can say, well, before I make any changes, I'm going to calculate the increase in the x direction that this ball is going to move. Okay? And that is going to be equal to what? Can anybody help me here? It's going to be equal to, and based on the rules we explain on the screen, is going to be equal to the hypotenuse of that triangle, which for us is the speed, is how many pixels it moves every frame, right? The hypotenuse times what? We're going in the x direction, so you can look at the whiteboard. It's fine. It's not cheating. Okay? Claudia. The cosine of what? Of the angle. Exactly. Okay? And similarly, I can say that the increase in the y direction is the opposite side of that triangle. So that's going to be the hypotenuse times the sine of the angle. And now that I know those two differences, what I can do is I can say here, well, I'm going to increase x by the increase in the x dimension, and I'm going to increase the location of y by the increase in the y direction. And if I do this, Now my circle is moving in that direction. Oh my God, Jose, really? Like you did this? We had that very similar effect before. Well, we did, but check this out. Now, if I change the angle from 30 degrees to 45 degrees, now I have linear speed of 1 pixel at 45 degrees. Now I can change it to 90 degrees, and it goes down, or I can work with any value of the angle. Okay? Oh, really? That doesn't look very exciting, right? Well, it doesn't, but it's going to get a little bit more exciting because before, something that we were doing is that, and this was on purpose, we will always draw in a circle because a circle is kind of symmetrical in every direction, so it kind of feels natural that it bounces all the way around. But now that we're working with something that kind of has direction, speed, and angle, maybe representation-wise, it looks more interesting to represent it as a square, because a square kind of gives us somehow an like an intuition of direction, rather than a circle that can just go in any direction, right? So I'm going to replace ellipse. I'm going to replace it by a rectangle, so that I start drawing, instead of a bouncing ball, I'm going to start drawing like a steering car of some sort. Okay? So I'm going to replace ellipse by the function rectangle here. Okay? And I'm going to go back to this, and I'm going to make the car much longer. Something like 50 and 20. Okay? So you guys now can see that I got my car, and the car is moving at 30 degrees. But what is wrong with this car? You guys see anything wrong with this car? It doesn't really feel natural, right? Like a sort of like drifting car, like it's just not great. Okay. So how would you fix that? I would rotate the car by how much? By the angle at which it's going. And what have we learned today that is useful for rotations? Working with two-dimensional transformations. So something that we can do is, before drawing the rectangle, something that we can do is, if we know that the car, if we know that this is the window, and that this is the location of the car, and that the angle is kind of like this, something that we can do is, before drawing the rectangle in x and y coordinates like this, what we can do is we can take the coordinate system, we can move it here, and then after that we can rotate it and align it to the angle at which the car is moving. And therefore, the rectangle is going to be aligned to whichever direction we're going. How can I do that? With the technique that we learned before. Okay? So for example, I can translate to the x and y coordinates of where this rectangle is. I can rotate the coordinate system a value equal to the angle at which this thing is. And if I run this code, you guys can see that it's not really working. Why? Where did my rectangle go? I made a mistake, and the coordinates of the rectangle, I forgot to change them to 0, 0. So look what's happening here. The rectangle should be drawn at 400, 300 or something. But if I move the coordinate system before to this, and I still draw the rectangle at 400, 300, then the rectangle is going to be somewhere here. I need to now that my coordinate system is here, I need to draw the rectangle at 0, 0, right here. Right? So I need to replace that with 0, 0. Okay? Ooh, that's looking much nicer. Okay? And check this out. If I change the angle to 45 degrees, now it's moving in that direction. And if I change it to minus 45 degrees, it's going to go in that direction. Okay? Okay, now things are looking better. Just for the sake of reference, what I'm going to do as well is I'm going to draw a straight line pointing forward so that I know exactly where my car is going, just for the sake of visual flavor. Okay? I'm going to draw the rectangle, and I'm going to draw a line from the coordinate system center, so 0, 0, 100 units in the x direction. And as I do that, you're going to see that I got a line that represents the direction at which the car is going right now. Okay? But that's kind of weird. Like, why is the line not at the center of the car? Why is on one side of the car? Because remember, if my coordinate system is here, this is 0, 0. So my rectangle, which by default gets drawn from the corner, right, is going to be this one. And the line that I've drawn from 0, 0 to 100 and 0 is going to show like this. So what would be convenient in this case is to change the way rectangles are drawn by default. Instead of drawing them from the top left corner, which is how processing behaves normally, we should probably change them and draw rectangles from the center. So that my car now looks from the center and has this line here. How can I do that? You guys are probably familiar with rect mode. At the beginning of my code, I can say that for the life of my program, I want rectangles to be drawn from the center. And if I do that, now this thing with a horn is attacking something else, okay? I don't know. Any questions? Nope? Okay, so what else? Okay, we got something going on here, but this is not quite working fully yet because it's walking and we can control the angle, we can control the speed, but we can't really, right now it's leaving the screen, okay? So how can we make it bounce back into the screen? First of all, what are the conditions that make this object? What are the conditions that we're checking against so that the car goes back into the screen? Let's work with the center. The center is easier for the time being. With the x is greater than the width, or when the x is less than 0, then we should bounce the car back in. But how did we used to bounce the ball before? We had negative velocity x, or if it was the top and the bottom boundary, we did negative velocity y. But we don't have velocity x and velocity y now. We just have one single velocity. What do? We flip that. We could do that, but look at what's going to happen. Speed equals negative speed. If I run this, the car is going to start going towards the border, but then as it hits it, then ping, 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 ping. Now it's going backwards because now we have orientation. Now it's not symmetrical movement. Now we have a front and a back. And maybe we don't really want the thing to back out. We want it to turn around and go in the other direction. What does turning around and going in the other direction mean? Rotate what? – 180 degrees. Very good. So how do we rotate the car 180 degrees? Huh? What do you say? We need to change the angle. If it's going at 30 degrees, what do we need to do with the angle? Add or remove 180 degrees so that it goes back. So if we have the angle, then what we can do is, for example, add 180 degrees. How many radians is 180 degrees? Pi. Radians are confusing, huh? We're going to talk about that in a second. So here we go, and boom, it bounces back. Okay? Okay, that works for 30 degrees, but what if it was 45 degrees, and we hit this boundary here? Now it's not working. So what do we need to do in order to make it work also with the bottom and the top boundaries? Huh? Because it bounced here. It kept going down and it bounced here. But we want it to bounce here. So what do we need to add to the code to make it bounce also on the top and the bottom border? If y is greater than the height, or y is less than 0, then what do we do if that's the case? Parker? Same thing, angle. We increase the angle or we decrease the angle by pi radians. Okay, so now it's going to hit the thing. And, okay, that looks good. But look at what we've done. Here, there's actually a lot of redundancy of code. For these conditions and for these conditions, we're doing the same thing. So now in this case, because we only have one velocity and one angle, we can kind of merge these two situations and then just say if x is blah, 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 or if y is blah, 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 then we need to flip the angle. So both situations work equally well. This is just for the sake of cleanness. In one single conditional, we can check for the 4 situations and then act accordingly. Okay?
If you turn that back on, yeah. If you, instead of the line, had, let's say, a second rectangle or a triangle, what would the center bounce off point be in respect to? Would it be the center of the first shape or the center of the entire thing?
It depends on what you want to check. Right now, the center of the bounce is x and y, which is the center of the rectangle. That's what we are looking at here in order to bounce. If you wanted the tip, like the front of the car, you would need to do some further sines and cosines here to figure out what, at each point, what this point here in relation to x and y is, with some sines and cosines. Okay? Okay, are we all good? Okay, but now, it's when the cool stuff is going to start happening. Okay? So now we have a really smart system that allows us to control the velocity and the angle of a moving object in a 2-dimensional screen. Okay? And right now it's automatic. It's just doing the same thing over and over again. But what would happen if we added some user input? What if us as users would want to control the velocity and increase or decrease the velocity and increase or decrease the angle of the thing? It's actually super simple. We already know how to read if the user is pressing the keys, right? So let's say that I wanted to control the velocity and the angle of this car with my, for example, the ASDW keys, okay, which are very popular for gaming. I'm going to start by implementing rotation with A and D, the 2 sides, right? So I can say if the user is pressing the key, if key press equals true, okay? If the user is pressing any key, then let me check which key is he or she pressing, and then if it's A or D, then I'm going to rotate the car. So, for example, if the key that the user is pressing is A, or you know that we have to check for lowercase and uppercase, just for the sake of safety. If the user is pressing A, what do we want to do with the car? We're going to rotate where? Left. And left is what? Counterclockwise. So how do we rotate the car counterclockwise? What can we change in our variables, in the values, to rotate the car counterclockwise? We can change the angle. How would we change the angle? Do we increase or decrease? Huh? We decrease the angle because remember that angles are positive clockwise. And since we want to rotate counterclockwise, we need to decrease the angle. So angle is going to be equal to whatever it was before minus a tiny value. So for example, 0.01. Let's see if that works. I'm going to rotate. I have my car, and then I'm pressing A, and woo! Huh? Hey! Right? Okay. What about rotating in the other direction? I can say, well, else if key equals lowercase e, d, or key equals uppercase D, then angle is going to be equal to angle plus 0.01, for example. If you guys want to use the cursor codes, the cursor keys, if you guys want to use the arrow keys instead, I forget what was let me check that out. Let's do the arrow keys instead. I think for you guys with Macs, it's going to work better. Give me a second. Okay. Okay. Yes. So we can replace this by saying if key equals coded and key code equals left, then rotate like that. Or if key equals coded and code is right, then rotate to the other direction. And with this, okay. And what about speeding up and speeding down? How do you guys think we can do that? We can increase the speed. We can add more conditions and say, well, else if the key is coded and the key code is up, then, for example, what do we have to do? What should we do to make it faster? Jasmine. Exactly. For example, 0.1. Let's try that. And else if key is coded and key code equals down, then speed equals speed minus 0.1, for example. And I can do that, and then I can click here, and I'm going to speed it up. And it bounces back, and bounces back, and I can speed it up, or I can slow it down all the way until it actually goes backwards. Yep. How's this looking? Are you driving the car? Parker.
I'm noticing that when I increase the speed, or like when I use an angle, it use the angle even though I've released the key. Why is that?
Are you wrapping everything inside of a key press?
Yes, I am.
Okay, then we can take a look at that in a break. Okay, Antonio?
Can you put this key press code, does it have to be there?
It has to be before, so you can.
Right, but does it have to be inside the draw function? Can we use that other key?
The key press function.
Yeah.
You can use the key press function, but because you want to, in this case, you want to be pressing the key, and you want to keep turning instead of just pressing the key and turning a tiny bit, just once.
I will have to like.
You would have to keep pressing. So in this case, it's more convenient. That's a really good question, actually. In this case, it's very convenient to use it in a continuous mode, right? You want the effect to be happening as much as you're pressing the key.
This is kind of, I mean, for these, it works, but like for the letters, it sort of fails.
Yeah, but that's a problem with Macs. The thing with Macs is that if you press certain letters continuously, you get this pop-up where the Mac OS system allows you to choose between different flavors of the letter with like tildes and like umlauts and whatever, and that blocks processing's ability to read the key. So if you want to do continuous keys with a Mac, you should either do arrows, that's why I chose to do arrows here, or you should try to use letters that do not have special flavors. Like, I don't know, H. H doesn't have any particular form, alternative form, you know? But A has a bunch, you know?
Gotcha. So I guess I used ASDF instead of, or WASD instead of left, right, up, down.
And that's why I was doing it, right? Okay. Okay, yes.
Is it accelerated? Like when you have it, if you like put your speed, you just hold it down.
Yeah,
and it just freaks out.
it accelerates.
Oh.
Okay. Okay, and this is very interesting if we want to have direct control over the car. But if instead we wanted to make it autonomous, what things we could do? We could, for example, something that we can do is we can cancel all the direct key interactions. And what we can say is that every frame, what we're going to do is we're going to calculate the speed, increase by the speed, check the bounce, and then on top of that, we're going to jerk. We're going to like jitter the car a little bit. How can we do that? Well, we can say every frame, what I'm going to do is I'm going to change the value of the angle by some random value between, for example, minus 0.3, 0.03, and positive 0.3. I'm just eyeballing these numbers. And check out what's going to happen. The car is going to start, but because every frame I am slightly changing the angle, the car is like, eh. I can make these values larger. You know, it's like a creepy, now it's not a car anymore, it's like a creepy ant. And I can speed this thing up here. You know? And if I took, and this is where the magic happens after last week, and if I took all of these logics, all of these values, and I packed everything inside of a class called, for example, the jittery car or the creepy bug or whatever, and then I instantiated a bunch of those with arrays, then something like this could happen. Okay? Which is what you guys are going to be doing today, this week, for the workout, which is, by the way, going to be the last workout of the semester. Okay? The workout tonight and for the next few days is going to be taking the class samples that I'm going to be going over today and turning them from one single object and global variables, packing them, everything inside of a class, and replicating a lot of those objects on the screen with an array. Okay? I will explain that in a second later, by the end of the class. Okay? Woo! We got over object-oriented programming. We got over trigonometry. Finally, we're good. Okay? Let's take a 5-minute break, and then we come over and we see more examples of physics-based animation. Okay?
Quick question.
Yes.
For the video game assignment, are you going to be going?
Okay, a couple things that I forgot to mention before is that we've already discussed the idea that angles are measured in processing clockwise because X is in this direction and Y is this direction, so accordingly angles are flipped, okay? And as in any other digital platform, angles are measured in radians. So if you remember, radians are this weird way of measuring angles where 2 pi radians account for a full circle or 360 degrees, okay? So processing comes with many internal constants that you can use to test directly. Instead of having to type 3.14, it comes with environment constants like pi, half pi, quarter pi, or 2 pi that you can use for just fetching those values directly, okay? And the way these ones are written, you see all caps and with an underscore, it's just a convention because these are usually referred to as constants. And it means they are similar to width and height and key press. They are variables that come with processing, okay? The only difference is that they never, ever change over the life of the program. They don't get updated. That's why, because pi never changes in this universe, at least I think, right? So the value of pi is never going to change, and it's noted with this uppercase notation and the green highlighting, okay? Also, remember that you have the function degrees to turn any value in radians 2 degrees, or you have the inverse operation, which is to turn any value in degrees to radians, okay? And that you can, trigonometry-wise, find the sine and cosine of any angle expressed in radians with those two functions, okay? For the sake of transparency, I would like to point out that there's these people out in the world who believe that whoever chose the value of pi as the constant for the circle was not in his best days, because if you think about it, it turns out that what is the formula of the length of the circle? What is the formula for the length of the circle? The circumference. 2 pi radius, okay? What is the form? Well, if you look at most of the formulas in mathematics and physics, they're actually multiples of 2 pi all the time. But on top of that, if you want to measure angles, so a full turn being 2 pi, it's kind of like counterintuitive because like, how many turns is 6 pi? 3. How many turns is 7 pi? How many degrees is 3/4 of pi? Who knows, right? So there's people out there who believe that if the constant for the circle would have chosen as the value of 2 pi, aka 6.2839, etc., right? And some people refer to it as tau, then much more of the mathematical formulation would have been simplified, but also the way to measure angles in radians would also be much simpler because 1 tau radians is how many turns? If tau equals 2 pi, then tau radians is 1 turn. 3 tau radians, 3 turns. 2.17 radians, tau radians, 2.17 turns, right? So it makes things much easier. Full disclosure, I happen to be one of those, and I advocate for the benefits of using tau in general. It's just makes things much easier if you just understand that tau equals exactly 2 pi. And I happen to celebrate every year Tau Day, which is when? June 28th. Very good, right? With some of my friends at Fathom Information Design, which are also true Tau believers. And for that same spirit, processing also comes with tau as its constant. So whenever you do angles, you can choose tau, and there is a constant in processing with the value of tau. You can check more if you're nerdy enough on these links here. Charlie? It is Taoism. And actually, you can go, if you want to learn more, you can go to taoday.com and read the Tao Manifesto by Michael Hartle, who's also aware about processing having tau as a constant. Okay. This guy here is Andres Colubri. His nickname is Code Anti-Code. He's responsible for most of all the shader that goes into processing, the shader language. He's also responsible for a lot of the Android for processing development, and he wrote a lot of the changes for the version 3. And this guy here is Ben Fry, is one of the creators of processing, and this is his daughter. Anyway, we've discussed trigonometry, we've discussed etc. Okay, if you want to learn a little bit more about trigonometry, there's a really good tutorial here in trigonometry, and there's Dan Schiffman's videos that I sent you. Okay. I happen to favor, I don't know why, but I happen to favor people who use tau. So up to you whether if you want. I do not make distinctions based on religion, gender, mathematical constants. It's fine. It's just sympathy, purely sympathy. Okay. Anyway, moving on. Let's talk about alternative ways of creating animation. Okay. We have so far discussed moving things in 2 dimensions, right? Either by having 2 velocities or by having a velocity and an angle, okay? And those have been really useful for creating linear animations, aka things that move linearly at the same speed in whichever direction, okay? We've seen ways of changing that speed by using the keys, right, okay? But very often, we will want to create other kinds of animation that has some kind of like acceleration and deceleration, because for 2 reasons. One, because it's very fancy and it looks really nice. So when you're using your iPhone, your notifications don't pop up like, and then they go like, right? They pop up like, and they pop out like, right? There's an acceleration and a deceleration, right? It's very fancy. It creates an interesting animation, but also it turns out that the mathematical rules to implement that are like extremely straightforward. So it's very cheap to create animations like that, okay? That kind of animation that decelerates as it reaches the target and accelerates very fast at the beginning but decelerates, is usually to refer to as easing, okay? And the idea is that if we were to go, for example, from one point to the other, the way we've been moving before is by moving a fixed unit every frame. So for example, 1 pixel or 2 pixels, right? Which creates this linear constant animation. But if instead of just adding a fixed value, we changed the rule. And we came up with a rule where we said every frame that I want to go from A to B, if every frame, instead of just adding a tiny bit to that distance, I change the rule, and the rule becomes I'm going to travel a fraction of the remaining distance to my target. Then what would happen is that if we start here, frame 0, and I say every frame I'm going to travel half the distance that's remaining to my point. The first frame I'm going to move very fast, but because on the second frame the distance is much smaller, half that distance is going to be slowing down and 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 slowing down. Okay? So if instead of working with addition, I work with fractions of remaining distance, I generate that idea of moving very fast but decelerating as I reach a target. Okay? How can I implement that? It's extremely, extremely easy. Let's start a new processing sketch, okay? And you guys please join me in, are we recording? Yes. Can you please join me in creating the basic scaffolding? So a setup function, a draw function, okay? I'm gonna create like the size. I'm gonna make my screen very large this time, like a 1400, and then some background color. Okay. The next thing I'm going to do is I'm going to draw a circle at the center of the screen, but all the way to the left. So the circle is going to start at 0, and y is going to be height half. And then the next thing I'm going to do is I'm going to draw that ellipse on x and y with 20 and 20. Okay? If I draw this sketch, I have a very large screen with a circle that is all the way here. But what I'm going to do is I'm going to animate this circle, and I'm going to make it move very fast to the right, but decelerate as it reaches this end. Okay? With an eased deceleration. How is that going to work? Well, how did we usually update the value of x? The way we used to do this was like, I'm going to update it by velocity x or by a constant value, whatever, 2, right? That generates constant movement. But that's not what we want now. What we want is, we want a rule where we say every frame, I want to move half the distance remaining to whatever I want to reach, which is the right end of the screen. So, how can I write here that I want to move x half the distance that is left to the right end of the window? How can I increase x by half the distance that is left? Oh my God, you guys are really low on coffee today, huh? The first thing we need to do is we need to figure out how much distance is there left. And if the circle is here, if the circle is here and this is x, right? How much is this distance here? Jerry, how much is this distance here? Is width minus whatever the circle is at any point. So width minus x, okay? So what we need to do first is we need to calculate the distance that is left to the target, width minus x, and then increase x by a fraction of this. So for example, half that distance. I'm going to multiply this by 0.5. Let me run this code and please look at the screen. Let me run this code and whoop, what just happened? Is this working? Let me check out again. What's going to happen? Whoop. It is actually happening. It just so happens that it's happening so fast because we run at 60 frames per second, more or less, that it reaches the end like even before we can see it. Okay? So let's tweak the numbers a little bit, and instead of navigating half the distance, let's navigate every frame just a quarter of the distance that is left. So instead of 0.5, 0.25. I'm going to do this again, and it's still really fast. I kind of see a trail here. Still really fast. Now let's crank this down like a lot. Let's do 0.05, like a 20th of the remaining distance. And now let's take a look here. You guys saw that? Let's even a little bit slower. 0.02. Take a look at what's happening here. Okay. Good? Okay, can you guys add some code to make the circle start from the top left corner and make it ease into the bottom right corner? Can you add like a couple lines of code for that? We start off the top left corner and we ease into the bottom right corner. chase your mouse. Okay, so very easy. Instead of starting y at half the height, we start at 0. And then what we do is that every frame we update y by the same fraction, 0.02, times the distance that is remaining to the bottom right corner, which in this case is height minus y. And if I do that, then okay. Okay. And Parker is very excited because he changed a couple things in the code, and he's making the circle chase his mouse. Instead of just a fixed corner all the time, he's making the circle chase his mouse. How do you guys think we could do that? Using mouse Y and mouse X. Very good. Where should we use those? So, Brooke, in the place of width and height. So if we have our screen and the ball is here and the mouse is here, the distance is the coordinates of mouse X minus X and the coordinates of mouse Y minus Y. So this is the distance, this is the distance, sorry, the other way around. And that's what we need to do there. Instead of the target location being the width, now it's mouse X, that's where we want to go. And instead of the target being height, is mouse Y. And check this out. And now my computer is really slow because of the screencasting, but now it feels like I'm kind of like dragging the circle around. And it's nice because it eases, it slows down as it reaches the target. Okay? Ooh. I promised today was going to be much cooler. Okay? Okay, how about making this happen, making the circle chase the mouse only when I am pressing the mouse. When I'm pressing the mouse. Not all the time, but only when I'm pressing the mouse button. How can we do that? Huh? We can just, if this is the code that makes the mouse move, that makes the circle move, then we only execute this code, the one that makes the circle move, only when we're pressing the mouse. So the only thing we have to do is we have to wrap this thing inside of a if mouse pressed equals true, then move the circle. Otherwise, do not move the circle. So you see, the circle starts there, and only when I press, it starts going my way. Okay? Or if I continuously press, if I keep it pressed, then it chases me constantly. But I can just okay? Huh? Yeah, it just stops because you stopped updating the position. It doesn't slow down, you're right. That would require extra code. Okay? And now, and this is, okay, what I want to do is, I want to press the mouse once, and then I want to kind of like set a target, as in like, I want the circle to keep moving to whatever I press my mouse, but I want to be able to move my mouth away, to move my mouse away, and the circle still keep approaching that point that I did set somewhere. So I want to be able to click here, and then make my circle start moving this way continuously, but then at the meantime, just move my mouse somewhere else. I want to be able to set the target of where the mouse, the ball should be moving to dynamically. How do you guys think we could do that? Jerry?
You set up like a two variable, like a dx, dy.
I set up two variables. Why? Why would you set two variables up?
Because you need to load the location of the click.
That's a very interesting point. I need to, when I click my mouse, I need to somehow keep track of where I click my mouse. So I need to store that information in two variables. And then what can I do with those two variables, Jerry?
You replace mouse x, mouse y with your, I guess, dx, dy.
Then I use those. Now the target is not anymore where my mouse is at any time, but it's those two variables that I set for the target. So for example, I can say here, I'm going to define two new variables called target x and target y. And I'm going to start them at 0. So both target x and target y are equal to 0. Okay? Then what I'm going to do is I'm going to take all the code that took care of moving the circle. I'm going to get it out of the if conditional because I want my circle to move all the time. Where I only want to change where it moves to. And I want to change where it moves to whenever I press my mouse. So what I'm going to do is here, inside of if mouse press equal true, I'm here, whenever I press the mouse, I need to store the value of where mouse X is and mouse Y is whenever the mouse is pressed. So I'm going to store that inside of target X is going to be equal to mouse X and target Y is going to be equal to mouse Y. And now, as Jerry suggests, every frame I'm going to replace this by target X and target Y. And let's see what happens. I'm going to run this code. The circle is on the top left corner. I'm going to move my mouse here and I'm going to click once. And then the circle keeps going to that place. And if I click here, and it doesn't matter where I move my mouse, if I'm not sure of what's going on, I can additionally here, I can just add like a very tiny ellipse on target X and target Y so that I can remember where I clicked. Okay? So for example, see how if I click here, this tiny dot shows up, which is the target. Okay? And then this tiny dot shows up here, and then, or if I drag, you see that the circle, the tiny drop, keeps changing places, and therefore the circle keeps chasing me dynamically. Okay? How does that look? Alex is liking this today. All right? Owen Parker is enjoying it a lot too. And guess what? If I took all of these guys and I made a class that kept track of mouse of the X and the Y and the mouse and the fraction of the easing, etc., then, oh, sorry. No. I'm disclosing stuff before, Okay, so this is cool. So now I have like a way of like telling this circle where it wants to go, okay? But to my taste, this is like a little bit too directed. And you know how I like to make things a bit more autonomous? I'm a roboticist, so I like creating behavior somehow, right? So I like this, but I think there's something more that we could add here to make the circle feel a bit more autonomous, that it has more agency, that the circle wants to do things on its own, okay? It still follows my lead, but whenever it gets bored, it can do things on its own, okay? So what could that be? I can, for example, implement a rule where I say, I'm going to keep pressing, and I'm going to be setting the target, okay? But if at some point the circle gets very, very close to the target, then maybe the circle can decide to set a new target randomly and start jumping to another direction. You understand what I said? We can implement a little rule where we calculate the distance to the target. And if it's under a particular threshold, then we just create new random targets and we jump again. And when we reach, we jump again. And when we reach, we jump again. How could we do that? Parker.
It's a conditional with the distance function.
Mm-hmm.
And if distance between x and target x and y and target y is less than, say,
1 pixel.
1 pixel, then
Let's do that. Let me start writing. If the distance between x and y and target x and target y, even though we know already, we could calculate this manually with the square root, but it's fine. We're going to do it this way, okay? If this distance is less than a particular value, for example, 1 pixel, then what could we do? What we're going to do right now is we're going to print a message here. We're going to say print line reached the target. And I'm going to print the frame count to make sure that I know. So for example, I click here and you see it's not there yet, but as it reaches, you see, now I get printing. I start printing messages here, okay? So I'm going to click again, and now I'm not printing the message anymore, but as it gets close, it's printing the message again, okay? Good. So we know now that this is working, but how can we now, once we reach this point, how can we make it jump to a new point? Target x equals a random value between which values? 0 and width. Very good. And target y is what? Okay. Let's check this out.
You have to assign it to random 0 width, or can you just do random width?
So look at what's happening. It's getting close and close, and as it gets very close, a new target is set, and then it jumps immediately. Then a new target is set, but since I still have this conditional here, I can still force myself manually to change target x and target y. So I can still override that behavior and still go for new targets. But as soon as the circle reaches the target, it's going to go like, I'm bored. I want to go somewhere else, right? And it's going to jump to a new target. It's going to set its own new random target, okay? Which, again, if we extend that notion to a class that contains all those properties and all those behaviors, and we propagate a bunch of this, we can get something like this, right? Every circle is setting itself new random targets, so they're traveling all around. But if I click somewhere, then they all, and as they start reaching that, they start getting new targets, like here, or here, or here, or here, or here, and when they reach, new random targets. Okay. Parker, you had a question?
Yes. So I noticed that you said between random 0 and width, is 0 necessary or no?
It is not necessary. Random function can take 0, 1, or 2 arguments. And depending on what you choose, here, the random function takes either 1 argument, so from 0 to high, or 2 arguments between those 2 extremes. If you don't set the low, then it's always going to be 0. Oops. Okay, any questions before we move on? We have 2 more types of animation to cover. You want to take a quick break and go back, or you just want to go for it and finish a bit earlier? Guys? More, less? Huh? Let's go for it. Good. I like that. Okay, so, a couple of remarks I need to do before. So this is the basic setup, okay? And you may have noticed that when I said that we were going to make a check when the circle approximates the target and when it is under a particular threshold, aka when it is very close to the target but not really on the target, then we're going to change to somewhere else. Why do you guys think I said that? Why do you guys think that I said when we get very close to the target but not when we get to the target? Does that make any difference? I usually don't say things in vain. Claudia?
It's just like moving in fractions, so it never actually.
Exactly. Are you guys familiar with the Achilles and the tortoise paradox? Okay, let me show you a video. If there is sun. Damn it. Hold on, give me a second. Which other thing?
No, in your setting.
Which settings?
Like playback device. No. And then choose this.
Yeah, it should.
It may also be muted on
Porters would have moved, so Achilles would have to cover that. 60-second adventures in thought. Number 1. Achilles and the tortoise. How could a humble tortoise beat the legendary Greek hero Achilles in a race? The Greek philosopher Zeno liked a challenge and came up with this paradox. First, the tortoise is given a slight head start. Anyone fancying a flutter would still rush to put their money on Achilles. But Zeno pointed out that to overtake him, Achilles would first have to cover the distance to the point where the tortoise began. In that time, the tortoise would have moved, so Achilles would have to cover that distance, giving the tortoise time to amble forwards a bit more. Logically, this would carry on forever. However small the gap between them, the tortoise would still be able to move forwards while Achilles was catching up, meaning that Achilles could never overtake. Taken to an extreme, this bizarre paradox suggests that all movement is impossible. But it did lead to the realization that something finite can be divided an infinite number of times. This concept of an infinite series is used in finance to work out mortgage payments, which is why they take an infinite amount of time to pay off.
But yeah, that is pretty much the similar concept. The idea is that if you are creating a rule where the movement is based off fractions of the remaining distance, theoretically, you would never actually reach the target because you're always moving a fraction of what remains to get there, okay? In practical terms, due to the problem of floating point precision in computers, when you accumulate a lot of tiny precision, there's a point where the computer cannot be as precise anymore. So it just actually snaps to that actual theoretical value. But that takes a lot of that takes a long time, and it may take a lot of calculations. So when you do approximation calculations based on an easing, it's actually a good practice to keep track of not the value that you want to reach, but whether if you're under a particular threshold, aka whether if you're very close to that threshold. Okay, you can keep track of that by either doing distance is less than 1, for example, or by keeping a a Boolean value that tracks whether if the circle has reached the target or not, and then update its position based on whether if that is true or false. Okay, if you want to know more about this, you can check the processing handbook, input number 4, mouse 2, and it comes with a lot of examples on this topic. Okay? Okay, so let's change gears a little bit and let's keep talking about movement. But this time, instead of like mathematical ways, numerical ways of mimic different kinds of accelerations and decelerations, what we're going to try is to figure out numerical ways of represent motion that is based off or is inspired by the physical world. Okay? So for example, let's go back and let's try to implement. Actually, let's do it. Let's spend a couple minutes implementing again this example of, or actually, let's spend a couple minutes implementing again the example of the bouncing ball in the two directions. Okay, but please do it with velocity x and velocity y. Okay, and I will explain in a second why this makes sense in this case. Okay, so please go ahead and start a new sketch and implement the setup, the draw, x location, x and y locations, and velocity x, velocity y, and then make the ball bounce on the screen in both directions. Okay, give it a shot. This is like calligraphy. You're going to know that program to the heart by the end of the semester. Hmm?
Do you have a specific size preference? Screen?
Nope, I do not.
So I have the x and y velocity set to the same thing. Is there a reason why you and yours set them to different speeds?
No, just random value. Okay, so we've done this example like very often. The problem with this example is that, yeah, it's a bouncing ball of sorts, but if we were to be a bit precise, there are many things that are not right with this example. For example, the only way a ball would bounce in such a way ever would be in space, in a vacuum, where there would be no friction and no gravity, etc. And or if we were looking at a, I don't know, like a disc hockey table with like infinitely slow, infinitely nothing friction, which is impossible technically. So the idea is that the world that we live in is full of forces that make things accelerate, brake, change velocities all the time, right? And if this example was a bit more inspired by the physical world, then many things would need to be changed or improved. So for example, imagine that we were looking at this window, and instead of looking from the top view, which might be the only way we'll get away with this, like asteroids, imagine that we were looking from a front view, right? And that the ball, which starts here, if this was a front view, the first thing that the ball would probably start to do is to start falling down, right? And why would it start going down? What is making it go down? Gravity. In the physical world, there's this thing called gravity that pulls things down, okay? And let's break that down even more. So if I release the chalk, okay, and I let it fall, can you guys describe the motion? Is this linear motion? Is this going down in constant velocity? No? It's free fall, which means what? It's accelerating. Why is it accelerating? Because of gravity. Because gravity is a force that changes. What is gravity changing in the circle, in the chalk? It's changing the velocity. Gravity is not changing the position, it's changing the velocity. It's increasing the velocity, because if I were to let this fall, theoretically, if there was no air, it would keep accelerating and accelerating and keep going faster and faster until it became a bullet of sorts, okay? That's not the case for the reasons we will see later. But think about this hierarchy of relationships. When we think of the ball, what we have worked with is with the position. Position that could be measured in meters, feet, whatever. We measure it in pixels, right? And so far, the basic force that we've been working with for the circle is to make it change positions based on something that we have defined as the velocity, okay? So velocity is a force that affects the position. If velocity is constant, position changes at a constant rate, right? And what do we measure velocity in the real world? Meters per second, for example, or miles per hour. What do we measure velocity in processing? Pixels per frame, right? But if we were to add something that makes the circle accelerate as it goes down, just with the same metaphor of gravity, gravity doesn't change the position, it changes the velocity. It changes the velocity, it makes velocity increase. So the same is going to happen here. If we want to add some kind of acceleration, for example, gravity is going to affect velocity. And then velocity will affect the position. Okay? And what do we measure gravity in the real world in? What is the value of gravity on Earth? 9.8 meters per second squared. So what will we measure acceleration in processing? Pixels per frame squared. And notice how as we go up the hierarchy of forces, what we do is we keep adding an extra temporal dimension. Okay? So acceleration changes velocity, velocity changes position. Okay? This hierarchy, the same exact thing, we're going to implement in. Okay? What are we going to do? Here, we're going to add something that I'm going to call gravity. Okay? And gravity is going to be a force that is going to accelerate velocities on the way down. So if it's on the way down, what is the sign of gravity going to be? Positive or negative? Huh? Just negative. Why? So if you go down, you're going positive. Damn it. So gravity, because processing takes y pointing down, gravity is going to be positive here. In the real world, is negative. So gravity, for example, is going to be 0.02, for example. Okay? And then check out what I'm going to do here. What I'm going to do is, when I update the position, I'm updating the position, which is measured in pixels, by velocity, which is measured in pixels by frame. But before that, I will need to change the velocity based off the gravity. Okay? Which velocity am I going to change with gravity? Y velocity. So velocity x, every frame is going to increase or decrease? Huh? It's going to increase. It's going to increase by the value of gravity. So first, I increase velocity by gravity, and then I increase the position by the velocities. And if I run this code, then you see, well, I think gravity is a little too low here. Let me crank gravity up. 0.1, okay? Whoop. Okay, that looks much closer. Okay. Antonio's liking this. What's weird about it?
The Y value doesn't go down every time as it bounces. It keeps bouncing back to the same.
Ooh, it keeps bouncing back up to the same height. And why is that?
When it hits the bottom, it just makes the velocity negative, so then it's just going up again. I
Uh-huh.
don't know exactly how
Yeah,
to
yeah.
fix that.
Yeah. So it is going down. Why am I not, for example, when I hit the bottom, why am I not flipping gravity? Because gravity never changes. Because gravity is always pulling down with the same strength. Gravity doesn't change on Earth. It's always minus 9.8, right? Same here. Gravity is always going to be pulling down. The only thing that changes is velocity, okay? But like they were pointing out, it feels weird because it keeps bouncing back up to the same height, okay? If I had a basketball here and I let it go, it would start bouncing, but at some point, it would start losing inertia and it would just stay flat. What in the real world is causing the ball to lose momentum and end up flat on the floor? Friction. Is friction. The ball is having friction with the carpet, is also having friction with the air. There's a lot of friction everywhere. And friction is slowing down the movement in every direction, right? So something that we can also add to our physics-based environment is friction, okay? Question here, what is friction? Is friction a position, is a velocity, or is an acceleration? And I want a good answer to this one. A recent answer. Is friction an acceleration, a velocity, or a position? It's probably not a position, okay? So, is it a velocity or is it an acceleration? Why?
It's an acceleration because it's changing the velocity.
Exactly. It's an acceleration because it's changing the velocity. It's slowing down things. Right? So, this gravity is an acceleration. Friction is also an acceleration. Okay? And there are many other accelerations out in the real world that we can think of. Okay? So, if I add friction to the system, I can add friction, and then what I will need to do is I would just have to slow down velocity by friction and slow down velocity by the friction. Okay? So for example, I could say friction is going to be 0.01, and then velocity is going to increase by gravity, but it's also going to decrease by friction. One thing to note here is that by convention, gravity is usually represented as the fraction that, sorry, not the fraction, the percentage that a particular thing is reduced by. So instead of doing, for example, 0.01, as I did with gravity, this time I'm going to go for 0.995, okay? So I'm going to reduce every frame, I'm going to reduce the speed by 99.5%, okay? And what I do is, here, every frame I'm going to increase velocity by gravity, but then I'm going to decrease velocity, I'm going to multiply it by friction. And because friction is a value that is very close to 1, but it's not really 1, every frame, velocity y is going to decrease a tiny bit. Does that make sense? If I run this code, now the circle goes down and down. You guys see what's happening there? And now, Richard, you see what's happening here? Look at what's going to happen. And Richard ran into this problem before today. And, yes, right? Am I good? Huh? Okay, we'll see. We'll figure that out, okay? But you see what's happening with friction, okay? It's up to you to decide what this friction is. You can choose a very, very tiny value for example, for the air friction, right? You can say air friction is going to be 0.9995, so something almost minuscule, okay? But I reduce velocity y every frame by the friction of the air. However, I can choose, well, it turns out that the carpet is very rugged, so this has a lot of friction. So anytime I hit the floor, I can choose to reduce the friction by a lot, right? So for example, I can say floor friction is going to be a value of, for example, 0.95, which is a lot, or 0.9, okay? And then I can reduce the velocity y by the friction of the floor every time I hit the floor. When is that in the code? Where is that in the code? Here. When I flip the velocity y, here's when I'm hitting the floor. So here is when I can at once reduce the velocity by the floor friction. So I can say velocity y times equals floor friction. And now you're going to see that as it goes down, velocity slows down but the bouncing part makes it slow down very much. When it bounces, it loses a lot of momentum, okay? And we're going to see that even stronger as the ball hits the floor and it starts, okay? You see? And it got stuck. Something that we're not doing is, if we consider that there's air causing friction and that there's carpet causing friction, we're only applying that friction in the y direction. And that's probably not right, because if we did that, then the ball would be infinitely moving sideways at least, right? So when we do air direction, we may want to add friction in the velocity x as well. Is for air friction, but especially when we hit the floor here, we may also want to decrease velocity x when the ball is hitting the floor, okay? So here, velocity x is going to be decreased by floor friction. And now things are going to start looking a bit more natural because as we hit this, it's going to decrease in that direction. You see? Probably we would also want to add some friction when it hits the sides. Okay, but you can leave that. You see how the ball is losing momentum in the x direction, right? And it's losing a lot of momentum now. And it's about to and it sinks. Okay?
Had something happen where it went from a very high bounce to just about no bounce all of a sudden?
Mm-hmm. Yep. Yeah. We're going to address that situation right now. Okay? Any questions about frictions, accelerations, velocities, gravities? Are we good? Okay. So let's address the situation. We're having a glitch here of some kind. The glitch is that as we start bouncing, at some point the ball hits the bottom and then it just sinks down. And to Parker, it's actually happened at the second bounce because it depends on the combination of numbers that you have. What is going on here? Well, it turns out that now that we're being super precise and super picky about all the interactions that are happening, we're creating a complex environment that has a lot of interactions between objects. Then, if that's the case, we need to pay special attention at what is actually going on in terms of geometry and in terms of bounciness and in terms of all the interactions. So for example, one thing that we haven't really accounted for is that, check this out. Where is my circle bouncing? Let me make the circle much larger so that we can notice that. If my circle was 100 radius, where is my circle bouncing off from? It's bouncing off the center, right? And that's not great because we want to bounce off the edges of the circle, right? So what is the first thing that we will need to modify in order to make the circle bounce off the border? The if statement. What would you change?
Well, I mean, depending on what the radius is, you can just say like width plus radius.
Okay, sounds good. So let's start being more programmatic, and I'm going to create a value of radius, which I'm going to set at 50. Okay, and what I'm going to do is here I'm going to set 2 times radius, 2 times radius. But now the rules for bouncing are going to change. And here, when I bounce against the floor, now I don't want to check the center, if the center is greater than height. What do I want to change now that I want to account for the radius? If I have this here, if this is my window and this is my, well, I don't want to bounce off from here. I want to bounce off from here. What are the coordinates of this point? The coordinates are x and y plus the radius. So that's the point that I want to check if it goes through. Okay? So if y plus the radius is greater than height, then, radius is greater than height. And let's see if that, oh, that looks much better. Oh, but it's still not working on the sides. Oh, you see the glitch? Okay, we're going to fix that, don't worry. Okay? Oh, quicksand. Okay, let's fix it on the sides as well. If x plus the width, plus the radius, and x minus the radius is less than 0, now it's gonna bounce on the sides also based on the radius, okay? Okay, but now we still got the quicksand, okay? And let's address the quicksand. So what is happening here? And for this one, I want to please call your attention because this is going to be, you have to be like, check out what's happening here. What's happening here is that imagine this is the ground floor, okay? And our ball, which is at some point here, is coming down very, very fast, okay? Imagine that the next time that we draw the circle, we update all these constants, the position, whatever, and at the next frame, the circle is somewhere around here. Okay? At this point, because it went past the bottom, these situations here trigger, and then the ball bounces all the way back up. Okay? However, there's a problem, because now we have added velocity, gravity, friction, whatever, blah, blah, blah. It turns out that when it bounces back up, it bounces back up less than it did, less than the distance that it came back from, right? So for this one, maybe it comes here, but on the next one, it bounces back and it stays somewhere here, maybe. Okay? So that's, and if that happens, we're kind of okay. But it might happen that we're bouncing back down so fast that it may happen that we bounce down so fast that on this one, we're all the way down here. And because we have so much friction, velocity, gravity, blah, 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 whatever, on the next one, on the next frame, when we bounce back up, we stay, because of all the frictions, we stay underneath the ground floor. You guys see where I'm going with this? Because since we now decrease the velocity y when it bounces back up, we may not reach beyond, and therefore that triggers again, and we flip velocity. That triggers again, we flip velocity, we flip velocity, we flip velocity, and that's why we keep getting the quicksand. Okay? Wow. But you're running into these corner cases because now you are good computational designers that are doing complex stuff. Parker.
So I'm having an issue where my the ball just stays on the left-hand side and doesn't move on the.
Same problem. Because you have frictions on the sides as well. Okay? So, how can we fix this? Any ideas? Oops. How do you guys think we can fix this? What would happen in the real world? Would the ball be here? No. It would never go through the floor, right? Therefore, it would never get stuck. But we are allowing it to go through, because in nowhere, the only thing we're changing is velocities, but we're not really snapping the circle to stay here if it at some point it goes too far down. So the solution to avoid the problem of quicksand is to, anytime we go past this border, making sure that we move the circle back up and we snap it to wherever it should be, aka hitting the floor, or if we want to be like really, really precise, calculate this distance and then move it up that distance, which is what would happen in reality. Okay? So, let's do that. If y gets too far down, where do we need to reset y to? We cannot let it just be somewhere under in the ground. Where should we reset y back to?
Y plus, height minus radius.
Height minus radius. This location, the location where the circle is just right tangent to the floor, is when this coordinate, the coordinate y, is height minus the radius. Let's see if we have fixed the issue. Have we fixed the issue?
Running into the issue where the x position of my circle is not changing at all. It's just staying along the left-hand side.
Where are you starting your circle? Hold on. Let's. Ooh. And then at some point, it just stops. because of all the frictions and all the decelerations and everything, which is a way more natural. So let's speed things up and increase frictions. So let's say the velocity x was greater and velocity y is none. Let's gravity, we want more gravity probably. Richard, you got it now? You think you can fix your fireworks now?
Probably, yeah.
Good. We can take a look at that later, okay? There's probably like something. Okay. Any questions? Okay, now that you're doing high-end stuff, you're gonna have to have an high-end eye to these kind of situations, okay? However, I'm here also and I have your back. I have experience in these things, so when you have problems of this kind, I will probably be able to assist you, okay? Any questions before we go on to the last thing? Okay, so, and I forgot, obviously. If we replicate this with a lot of circles, with a lot of different frictions and sizes, etc., then we can create a simulation where we have all these like bouncing balls with each other. They all have frictions. They all slow down as they reach the floor, etc., etc., etc. Okay? Yes?
Is it possible to have elements respond to a movement of the window? As in, if you drag your window, have things move?
That's a really good question. Off the top of my head, I don't know how I would do that, but there has to be a way. I'm gonna look that up. Yeah, because the thing is, like, mouse X and mouse Y are not tracked as soon as you leave the window. So you have to mess with the system, which sounds like an interesting challenge to me. You can have a fake window, that's true. But then, would you be able to drag the actual window with a fake window? Okay. I'm going to take a look at that, okay? Okay, the last thing I want to talk about, and perhaps I'm going to go over this idea conceptually. The last force, or the last physics-based interaction that I would like to describe today is elasticity, okay? And this one, I'm going to go over it at a high level, and you guys can check the examples on the file. But the idea is that elasticity is just as any other of the forces we have described here, okay? And it is an acceleration also because it changes the velocity of things. So for example, how does elasticity works? Elasticity works based off something called Hooke's law, which was, I believe Hooke was a mathematician in the 18th century. And what's interesting about elasticity is that it's a variable force that depends on the direction, but it also depends on length, okay? What do I mean with this? Imagine I had a box of springs, okay, and I pull a spring out of the box, and I hold it between my hands with the same length that the spring contains, okay? So if the spring is this long, I hold it just like this. What pressure, what force is the spring pushing my hands? Which way is the spring pushing my hands? If I'm just holding it as is, there's no force. The spring is doing nothing on my hands because the length of the spring has not changed, okay? Okay, now imagine that I start pulling the spring away. What force is the spring putting on my hands? It's trying to bring my hands back together, right? So the force of the spring is in the other direction from where I'm pulling, okay? And what if I push the spring inwards? Which direction is my spring springing back? Outside, okay? So again, depending on the rest length, okay, of where I am setting myself against the rest length, then the direction of the force is going to be different, okay? Also, on top of that, if my spring is this large and I pull a little, is the force going to be the same as if I pull really a lot? No. Which one is going to be stronger? As the more I pull, the stronger the force is trying to bring my hands back down, right? So the force is also directly proportional to the difference in the rest length. And the same goes if I push the springs together, if I push the spring inwards, okay? And third component here. If I have a box full of springs, imagine that I have a really thin spring, the kind that you just throw over the stairs and it starts going down, etc., right? If I pull and push that one, is the force going to be the same as if I grab this spring that is used for car shocks and like with a really thick bit? Like, there's also something called stiffness on springs, which is basically a factor that makes springs just tougher to pull or push based on their physical whatever, okay? So elasticity is a force which we can imagine as a spring, is a force that depends on the difference in distance from the initial rest length, but also depends on a factor called stiffness. And the direction will be proportional to where I'm pulling or pushing from. That is represented by what's called Hooke's law. The force of a spring is inversely proportional to the stiffness factor, which is just a number, times x, which is how much the spring has changed based off its initial rest length. The farther apart I pull, the stronger the spring is going to pull back, okay? And it's a force. So you can calculate the force based on the stiffness plus the stretch, and then affect the velocity by the spring force and the gravity and the friction and any other acceleration that you want, and then use the velocity to change the position in that same hierarchy of interactions, okay? So, for that matter, and you can check this example at home. Oh, what is this? Yeah. So I can create, for example, something that looks and feels like a spring. There's also gravity in this exercise, right? So this ball has a mass, and the mass is what's pulling the spring down. The spring also has a rest length. But if I move my mouse around, this spring is bouncing back and forth because it's based on the direction of the mouse, it's based on the direction of the circle. And if I replicate this with a lot of those, then I get this funny, playful, whatever. I don't even know what this is anymore, but it's a lot of springs and a lot of balls. And woo, woo. Okay? Okay. So with this, I'm going to call it a day. Okay? You guys can check out the examples at home. It's really easy. And otherwise, do you have any other questions before we move on to homework? Okay, so let's do homework. So, homework. The first one and the last one is going to be the object-oriented workout. Okay? What does this mean? What I want you guys is to train and practice what we did last week, where through classes we were able to create a concept, right? The concept had certain properties which we represented as variables, and the concept, aka the class, had certain behaviors that we represented with functions. Okay? We gave them names, and then by creating this class as a concept, we were able to instantiate objects, particular objects with values for those properties, and then have an array with all of those interacting in the screen and doing fancy things. Okay? So what I want you guys to do today is to put that to practice. So it will be probably useful that you go back to last week's notes and perhaps last week's video. And if you need additional help, I can share some Dan Schiffman videos on classes and objects. That will be super helpful as well. And what I want you to do is I want you to practice that by taking the 4 main examples that we have developed today in class. The first one being the creepy car that navigates around. The second one being this ball that goes to targets but then jumps randomly as well. The third one being the ball that bounces off with gravity. And the fourth one being this ball that is hanging from the mouse with a spring. Okay? Those 4 examples, you have them in the notes. You also have them as they are working perfectly in the workout sample files. Okay? So you have the 4, the motion easy, motion gravity, motion springs, and the trigonometry example. Okay? What I want you to do is I want you to take each one of those examples, which are implemented with the global variables and with global functions the way we've done it in class. And I want you guys to take all that functionality and all those properties and encapsulate them inside of a class. And then in the main program, instantiate an array of those objects and have a lot of these objects on the screen. Remember that when I say objects, I mean objects as a very loaded word in computer science. Object as an instance that is coming from the class. Okay? You will read instructions on how to do that, but if you have any questions, you can see an example that comes with the sample files today. Here in the example, you can see an example of what I mean by before. That would be the bouncing ball, which is velocity, radius, blah, 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 whatever, that is before. And then the bouncing ball class is the exact same example, but what you've done is you've taken all those properties, you've created a class, you have created properties, a constructor, behavior, whatever, and then you have instantiated in your main code an array of those objects, which you create, you construct, and then you maintain with a for loop every frame. Okay? This technique is going to be incredibly useful for the main assignment of this week's, which is going to be the video game. Okay? So, and for this workout, perhaps you want to use a little bit of your creativity, and maybe you want to add a little bit of your own by adding colors to the objects or changing somehow the behavior. It's up to you. Okay? You can have some fun with this one if you want. You can make the cars different. You can turn the cars, instead of being cars, they can be ants, or I don't know. It's up to you. Okay? The submission is very simple. You just take each one of the 4 sketches, you save them with the same name, and you add the suffix class. Then you do all the operations you need to do. You pack everything, the 4 sketches, in a zip file, and you submit them to the link as we usually do all the time. Okay? Any questions about that? We're good? This is the very last workout of the semester. No more. Okay? Actually, that is not true. We do have a last workout, but let's take a look at that. The last workout is this one. It's a feedback survey of this class. Okay? What is this about? You guys and myself have been working together already for 5 weeks. So I kind of know more or less where each one of you is somehow. And you kind of know me already in how I teach the class, how I like building examples, how I use the notes and the video and the class samples and the assignments, and to try to make you guys learn and be more creative, okay? And I do this, I teach because, yeah, they pay me money, whatever, but it's not that great. I shouldn't say that in the camera. But anyway, I mainly do this because for me, as a researcher and as a person who's interested in fostering computational creativity, for me it's very interesting to learn how can I make this experience better and how can I transmit these ideas in a more optimized, easy, and better way for you to understand them, okay? And here in school we have Trace, which is a system of giving me feedback. And Trace is good for certain things, but it doesn't really give me the information that I need, which is particular to this class, which is particular to code, which is particular to design assignments, so that I can make this better and communicate this better to you. I've been teaching this for the course of 3 years already. I think it's not too bad, but there's always room for improvement. So I would like to hear your opinion, your sincere and honest opinion about how the class is, how you're enjoying it, how you're disliking it, and what things perhaps you could propose that we could do to make it better. Because we still have another semester. We still have half semester. So maybe there are things that we can still change and adapt to how you're feeling about the class. Okay? That's why I am asking you to fill in a survey. The survey is very simple. You're going to go to this link here, okay? And then you're just going to fill the survey in. I'm going to give you credit for this, okay? It's going to be graded, okay? The thing with this survey is that it's mandatory. You have to fill in the survey. I just ask you to do, okay? But it's also anonymous because I really want to know your opinion and I don't want you to be afraid of me knowing who you are, which makes it a kind of a problem because if I want you to do it but I have no way of tracking whether if you're doing it or not, then how is it mandatory, okay? So the way I came up with to figure out the problem is that the survey is anonymous, so you're not going to put in your name, but once you finish the survey, you're going to be, and if you finish it successfully with everything in there, you're going to be given a small riddle, okay? So once you solve that riddle, then you're going to go to this other link where you are going to put your name, and then you're going to fill in with the solution to the riddle, okay? This is a way for me to know that you've reached the end of the survey and that you've been prompted with the riddle, and then just submit the response to the riddle, okay? That's a way for me to track that you've completed the survey, okay? Any questions about that?
Is this also for this week or?
Yeah, this is also for this week. But this is probably going to take you like 3 minutes, okay? And also, the deadlines for these workouts were 2 days, so it was, but I'm going to extend them all 1 extra day because we have the makeup class on Saturday. So for you guys to come to the makeup class, relax and without the stress of the deadline, these deadlines are extended 1 extra day, okay? Any questions? The riddle is going to take you maybe 5-10 seconds of Googling, okay? And even if you don't find the answer, just write like, oh, you were giving me this question, but I couldn't figure it out. That's also fine, okay? It's not about the solution to the riddle. It's just about knowing that you have completed the survey, okay? Any questions? Yes. Yeah, so here it says Friday night, then it's Saturday night. They both have the same deadline. Yeah. Okay? Okay, and the assignment is going to be the video game. Okay? Let me, sorry. So what are we going to do? This is going to be the last assignment of the semester as well. It's going to be the midterm assignment, okay? After this, there's going to be no more lectures, there's going to be no more workouts, no more assignments. The only thing we're going to do is we're going to do final project. And actually the quality and the pace of the class is going to change dramatically because I'm going to stop giving you content and then I'm going to start working more on a one-to-one basis with each one of you, mentoring your own personal projects, okay? But before we reach that, I want you guys to go through the exercise of putting together a complex project with a lot of elements, a lot of objects, interactions, rules, interactivity, whatever, which is a small video game. Okay, video games are a fantastic application of all the techniques and all the ideas that we have seen so far in terms of technical implementations, but also they give you creative space to design your own interactions, your own rules, your own playfulness, your own graphics, your own whatever you want to do, okay? So, what are we looking at here with this video game? We're not looking at Call of Duty, we're not looking at Halo, we're not looking at high-end first-person shooters. This is not what we're looking at here, okay? We're looking at simple, low-key video games that have simple rules, simple interactions, but playfulness and evolution of the game is based off these really tiny interactions between elements, okay? So what I have in mind, which might be different from what you have in mind, and that's fine. What I may have in mind is like things closer to perhaps like the early 80s video games, like, I don't know, Pac-Man, Tetris, Arkanoid, Pong, those kind of like simple games that had one or two rules, but it turned out that the combination of them was really interesting and engaging, okay? Or in more modern terms, I don't know, Brick Breaker or like Candy Crush or like those kind of like simple 2D games where like there's very few rules, but like they're engaging and there's like an interesting evolution, right? You are welcome to get inspiration by old school video games or simple video games. Again, I'm thinking of our Asteroids, Space Invaders, those kind of things. But what you're even more welcome to do is to find personal twists or to give those video games a particular angle of yours, which brings it to a more experimental side, or that it gives it a new version that may or may not be interesting, okay? Maybe you try tweaking a little bit the rules of Space Invaders and making the invaders shoot back at you. I don't know. And is that cool or not? Is it too much? Whatever. I don't know. But let's try it. Design is a lot about trying things and then being your own self-judge of like, oh, this actually made sense. Oh, it's much more fun. Oh, it's actually too much. It doesn't, right? So if you're going to do Snake is actually not so straightforward to implement, but if you're going to do Snake, then what can we add or what can we change in Snake? Can we like have two snakes at the same time? Can we, as soon as we get very long, can we like split in two snakes and then like have like different controls for them? And can we reunite them somehow? Or there's things falling and I'm gonna be catching them with the basket. Like what happens when the basket is full? Should I just drop all the elements somewhere and then keep catching? Or I don't know, or like Brick Breaker. Can I think of a multiplayer Brick Breaker? 2 players at the same time? How does that work? Is it a competition? Is it collaboration? Are they one against the other? So how can I rethink Brick Breaker? I don't know. These are the kind of questions that would be interesting to explore in this video game. Or, even better, just come up with your complete new, unique concept of a video game, if you are invested in it, okay? We've had very successful and very interesting video games. And also, if the video game is good enough and it has like depth, maybe it could become like the basis of your final project, if you're interested in doing a video game as a final project. That is also a possibility, okay? But for the time being, let's try to keep it contained as a 2-week project, and then we can take it from there, okay? So, what are we looking at here? Minimal requirements are going to be the header section with all the information. Their game has to have some form of a splash screen with your game name and perhaps with some instructions how to play with it. But again, I refer back to my own opinions about this. If the game is so clear, so intuitive, so obvious that it doesn't need instructions, that is a really good rule of thumb, okay? Your game is designed in a way that it conveys some sense of progress. This is really important. When games are monotonous and they are the same thing over and over again, people get bored. They're not good video games, okay? Good video games are games that give the user 2 things. A sense of increasing difficulty over time. So if we are making balls bounce off the screen, maybe we start with one that is very low, but the second one, when it comes in a bit faster, the third one comes faster, and at some point it's really hard to manage, right? That's what interesting games are about. But also, interesting games give a sense of progress because somehow you reach milestones that give the player a good feedback. Whether if that is score, which is usually pretty boring, or levels, which starts being more exciting, or some kind of rewards in the form of like icons or images or music or whatever, then those things start making the game way more engaging, okay? So if the game conveys some sort of idea of progress or goal, or even perhaps you create a game that you can finish. There are games that are endless, but there are other games where you finish the game, you beat the game. There's a final boss, you kill the boss, you're done, right? Those things can be all implemented and should be part at least of the game, okay? Whether what that means in your own particular game is up to you as designers, okay? Your game should be implemented at least somehow with one class somewhere. And I really don't see how you would do it otherwise, okay? And your game has to work, okay? This is very important because, and this will be very important for the final project as well, you're going to engage in a project that's going to be more and more complex, okay? And the more you start adding variables and the more you start adding objects and the more you start adding interactions between them, you're going to start noticing that things are going to start breaking, you're going to start getting errors, and you're going to get stuck often. That's what Jonathan and I are here for, to help you with the technicals and stuck you, okay? But very often, you will implement some changes, you will break the game, you will try to undo those changes, and you will have forgotten what those changes were, and you will not be able to go back to a function, to a version of your game that works. Without that feature that you wanted to implement, but even without it, you will not be able to go back, okay? So, it is very important that you keep backups. We're not going to teach versioning in this class. So, the old school way of versioning things is just like, when I implement a feature and my game works with this new feature, I save this version 3. I put it in a folder and I keep it saved there. And then I start with version 4. I add more features, I reach a state that I like, I save version 4, I copy it in a backup folder, and I start version 5. Okay? Keep copies of the progress of your game in working stages. Because if at some point you break something and you need to go back, you will need those. Okay? And I will not accept video games that I cannot execute. Okay? I will accept games that in some weird corner case scenario, maybe they break and they yield an error. It's not desirable, but I will accept that. I will not accept games that I cannot execute or that they fail right away. Okay? So you need to be very clean and very orderly with your code and save copies of your working versions somewhere. Okay? This will be especially important for the final project. I've had, unfortunately, one student who came to the final review with the project not working. I told her, but it didn't work, and it was a really unfortunate situation, okay? I don't want you guys to go through that. Okay, and if you want to walk the extra miles, there's a lot of things you can do in the video game, okay? Your game may have some sort of a scoring system that indicates progress, but again, for me, that's kind of like quite lame. I think that progress is much better conveyed as levels or difficulty or rewards or something. Score is, it's just a number. It's not fulfilling. Okay? Your game increases in difficulty as you progress through it. Your game maybe allows multiplayer control. Maybe your game is about multiplayer. It's so intimately multiplayer that it cannot be thought as a single player game. Okay? And any other thing that you want to add here is more than welcome. Your game uses images instead of drawings. Your game uses sprites, animated GIFs. Your game uses a lot of sound and video. Your game uses the webcam to track gestures. Your game has random levels that are generated procedurally, like Minecraft. I don't know. But anything that you can think of, and that it works, and it makes your game exciting, that is very welcome here, okay? Remember, The ultimate goal here is not nice high-level implementation of any technical skill. What we want is games that are engaging, that are fun, and that make people want to keep playing that game as long as possible. If your game is boring, is predictable, is monotonous, is buggy, is not intuitive, is unclear, okay? So think about what you want to do and what are the rules of what you want to do. And then the technical aspect, Jonathan and I will help you put it together, okay? What we're going to do is we were going to have a session of hands-on building a video game from scratch. The basic video game is going to be Pong. We were going to have that next week, but because of this situation, we're going to change that to having that on Saturday instead. I really welcome you to come on Saturday, but if you cannot for any personal reason, I'm still going to record the thing on video, okay? The way it's going to work is for this video game, I'm going to allow you, if you want, to work in pairs, okay? So you will be able to group code. However, if you choose to work in pairs, then my requirements for the level of complexity and polishment and graphical outcomes, etc., will be more demanding. How much? Approximately twice, right? And so you may choose or not choose to work in pairs. It's up to you, okay? Working with people is nice, and you learn a lot of things. So if you want to give it a try, I encourage you to, okay? And the schedule is going to look like following. The next week, we're going to be doing hands-on, so this Saturday. But before that, I want you to go to this link and submit a one-paragraph description of what you want to do, okay? So I want you to tell me, I want to do something like asteroids, but instead of asteroids, it has Owen Wilson's face, and it's Ben Stiller who's shooting, and he does Magnum, and then it gets like, oh, you guys are too young for Magnum. I don't know. And you make like an overall description of like what it's about, what the basic rules are, and what is inspiring you, okay? You're going to submit that description here in the form, and then I will give you feedback on like, oh, I think that's cool, oh, I think that's probably too much for 2 weeks, oh, I think that's interesting, but try to bring your own angle, or try to tweak some rules from the traditional version of that video game, whatever that is, okay? I will try to give you some feedback so that by next week, you can start working on the game with some direction, okay? The way we're going to keep that is that we were going to do some feedback one-on-one next week, but since that's not going to happen, maybe I will extend the deadline a week, and then in 2 weeks, we can just have lab time here, look at the code, and then submit the thing in 3 weeks, okay? Maybe. Let's shoot for having it like really well in 2 weeks' time, and then we can take it from there, okay? In the other section? Ooh, I had not thought of that, but yeah, I don't see why not. Yeah, okay. But what about the deadline? The deadline is going to be this class then, okay? Is that cool? Okay. Who are you thinking of? Matt? Okay. Okay, sure. Any other questions? Good. Are you excited? Do you think that you have an idea what you want to do? What do you want to do?
Oh, no, I don't know what to do.
Parker? Owen Wilson?
Maybe.
Charlie?
Still considering.
I think I'm going to do that too. Mike? Excited?
Oh, yeah.
Okay. Okay, guys. Thank you very much. Have a good weekend, and I'll see you on Saturday.